So in the previous slide, whatever analysis we did, we had assumed one mathematical statement. We will now focus on that statement and try to prove that. So it can be viewed as an exercise. So consider two functions. Consider lambda is and if is, where is belongs to the interval 0 to 1, such that excuse me, such that lambda 0 is equal to A, lambda 1 is equal to B, A, B are arbitrary real numbers, and f of 0 is equal to 0, and f of 1 is equal to 1. Then show that for every such lambda of s, there exists a function f of s satisfying above properties above conditions such that lambda s is equal to E times f dot of s for some real constant, say for some E, for some real constant R, E, okay? Now I will be discussing a general method of answering this question. General method, and the method uses Fourier transforms, a good way of parametrizing functions which are continuously varying in its argument is to Fourier transform them. But then the coefficients become discrete, and then therefore we have a bunch of discrete countable set of, though infinite number of set of real numbers, and then we can do certain analysis. So the general method is use Fourier transform. However, because none of these functions, lambda and f, is periodic, Fourier transform is usually done for a full periodic function. None of them is periodic. Lambda satisfies periodicity boundary conditions A and B. F satisfies boundary conditions 0 and 1. The Fourier transform of such functions is not straightforward. So what one can do is to write, we separate out each of these functions lambda and f into two parts, where one part takes care of these boundary conditions, and that part is, the Fourier transform of that part is subtle, and we will not address, we would like to avoid that subtlety in our analysis. But the other part, it will be having periodic boundary condition, and therefore Fourier transform of that is straightforward. So given that discussion, let us define, so okay, let us separate. So then let me write, in order to avoid, okay, given, okay, let me write down what I just said. Given that the functions involved are not periodic, their Fourier transforms involve certain subtleties. I will explain what those subtleties are. To deal with that situation, to deal with this situation, we separate the function, we separate out the function in two parts. In two parts as follows. So lambda s can be written as some x s plus delta lambda of s. Okay, such that x takes care of the boundary condition of lambda, and delta lambda is periodic. So here x of s is a fixed integrable function. Now, choice of x is not unique. We have seen this. Earlier in the calculations of. Okay, I have positioned it in a wrong way, so let me just move it up. We have seen similar. We have seen it before doing such a thing when we calculated the path integral for free particle, where x mu of s were separated out into classical solution plus certain periodic boundary condition satisfying fluctuation, and that classical solution was a fixed choice. But in order to do the path integral, in principle, you do not need to choose any particular, any specific function. You need to choose a suitable one. So let me tell you what that suitable conditions are. So first, appreciate that this choice is basically choosing x, choosing a specific x is equivalent to choosing a specific point in the configuration space, in sigma, in the space of functions lambda, that sigma. And delta lambda, consequently delta lambda of S represent variations around that point. So therefore, since you are doing the integration of the entire of the entire space, you could choose any fixed point and integrate the fluctuation around that point. So the choice of the fixed point is not unique, obviously. So now X does not satisfy this periodic boundary conditions, but now if you do a Fourier transform of such a function, we will look at one particular example. If you do Fourier transform of such a function, then there are subtleties involved in the following sense. So Fourier transform involve subtleties. Fourier transform involves subtleties in growth of coefficients. So suppose you write x of s is equal to x0 plus sum over n greater than or equal to 1 xn c2n s. So I'm simply using Fourier's theorem here, and xn prime is 2n s, where c2n s is cosine 2n pi s. So this is s in the interval 0, 1. This is sine 2n pi s. So you can look at the Fourier's theorem. It is described in depending on where you are looking at the argument. This s can be x by L, where L is the range, x is this. So if you can map that ratio to s, and then you can check that this is how Fourier transform, Fourier expansion happens for a function like this. Now you see at s equal to 0, this is 0 and this is 1, and so s equal to 0 and s equal to 1, also this is 0 and this is 1, because both of them are periodic, and therefore this satisfies naively. What is naively? Naively means what? I mean, here the naivety relates to the fact that you are assuming a normal growth of the Fourier coefficients naively. So let me write it down explicitly. For normal growth of coefficients, x will satisfy periodic boundary conditions. However, when xn and xn primes have special growth property, it is possible to achieve non-periodic boundary conditions. So there will be an exercise given in the assignment. We discussed certain. Okay, never mind. Let me withdraw that statement about the assignment. Here we will not discuss how exactly this different types of growth properties of different types of coefficients, non-trivial coefficients for which the boundary conditions are non-periodic. We might do certain exercise in assignments related to that, but I'm not sure about that yet. But here, for the purpose of showing this statement, we would like to avoid that analysis, and therefore we have separated it out, and we will avoid doing Fourier transform of it. This is a fixed function, and this fixed function is chosen in such a way that it is integrable. We can integrate it, and then what one can show is the following. Then this delta lambda will have normal Fourier transformation as usual in like this. We'll have a Fourier expansion where the coefficients will have no special growth property. These are normal, and because they are you don't need any special properties for the growth properties for the coefficients, because this function satisfies periodic boundary conditions. So given that, how would you write, given this expression, what would be the corresponding fs which would satisfy this? So the solution is that following. So given this form of lambda, we choose, given given the above form of lambda, we choose f of s to be y of s plus delta f of s, such that y of 0, y takes care of the boundary condition, which means y of 0 equal to 0, y of 1 equal to 1, and delta f0 is equal to delta f1 equal to 0. So delta f is periodic, such that we choose f to be this way, such that y s is given by the following. Y of s is given by 1 over e times integral ds tilde 0 to s x of s tilde plus integral ds 0 to 1 lambda s, basically the zero mode of the Fourier transform of lambda. Okay, so what it means is that this separation, we had a separation of the lambda in x and delta lambda. Correspondingly, we have a separation of f that we need to choose in order to satisfy this condition. We are trying to, given a lambda, we are trying to find f. So f also has a corresponding separation like this, where delta f has a normal Fourier transform, Fourier expansion, which means if you Fourier expand it, the coefficients will have normal growth. But along with that, we have a function y, which can be explicitly constructed from x of s. Whatever x we choose, since we have chosen it to be an integrable function, we should be able to integrate it and like this 0 to s. So this becomes a function of s, and plus another term s times the zero mode of lambda in its Fourier transformation. Okay, and this is the first thing. So we are choosing this. Number 2 is that both delta lambda of s and delta f of s admit normal Fourier expansion. By normal, I mean that the Fourier coefficients have normal growth, generic growth, not any special growth. Both delta lambda and delta f admit normal Fourier expansions, and Fourier expansion of Fourier coefficients of delta f and e are given in terms of Fourier coefficients of lambda of s. So how this is actually of delta lambda of s. This is actually straightforward. So just this can be shown explicitly. Delta lambda, write delta lambda as lambda 0 plus sum over n greater than or equal to 1 lambda n c2n plus theta n s2n. Because delta lambda is 0 at the boundaries, one would have lambda 0 plus sum over n greater than or equal to 1 lambda n equal to 0, and delta f should be f0 plus sum over n greater than or equal to 1 fn c2n plus gn s2n. It also satisfies the same conditions on for the coefficients, which means f0 plus n greater than or equal to 1 if n is equal to 0. Then given this, from here we know we can calculate DDS of delta f, and that's given by sum over n greater than or equal to 1 minus 2 n pi fn s2n plus 2 n pi gn c2n. Then you have to show that f dot is equal to, this is part of f dot equal to 1 over e lambda n. Therefore, imposing f dot is equal to 1 over e lambda would mean that fn is equal to minus theta n divided by twice n pi e. So theta n is a Fourier coefficient of lambda. Fn is, we are finding that from it, and gn equals lambda n over 2 n pi times e, and y is given by, as I said before, integral ds tilde x of s tilde 0 to 1, and the second part is nothing but lambda 0 over e times s. So see, fn, gn, y, these are all parts of this describes f. They all describe f. They are parts of f, and they are given in terms of theta and lambda and x s tilde lambda 0. These are properties of obtained from x from lambda. And so one thing that is still left is E. E has to be given in terms of the properties of lambda. So this expression automatically satisfies the boundary condition. This automatically satisfies the boundary condition at s equal to 0, y 0 is equal to 0. Second term is 0, of course, and this is not 1, this is s, and at s equal to 0, this is 0. Now y equal to 1 boundary condition, y1 equal to 1. So use y1 equal to 1 to calculate E. So y of 1 is equal to 1 over E integral ds tilde x s tilde 0 to 1 plus lambda 0 over E. S equal to 1. I'm setting s equal to 1 in this expression, and that must be equal to 1. And this tells you that E should be equal to integral ds xs, basically the 0 mode of the entire function. Okay, so that tells you how to construct f given lambda. So to summarize, you take lambda, divide it into two parts, and your therefore your data that you will use to construct f is this function, which is integrable, and the Fourier coefficients of lambda. Using x and the Fourier coefficients of lambda, one finds the Fourier coefficients of f this way, and f has an additive piece y and delta f. So these are the Fourier coefficients of delta f, and this is the additive piece, and this is E in this that appears in this equation. Okay, so that is how it is constructed. And okay, I must finish it here. Okay, before yeah, okay, so this is one slide and this is the other.